topic is linear approximation, aka more practice with writing equations of tangent lines. To find a linear approximation, write the equation of the tangent line at a nice x value close to the one you want. Plug in your x value into the tangent line and solve for y. All right, we're going to do example 1 and 3. Find a linear approximation. Okay, so if we see those words, also think equation of tangent line. Think point slope. So let's write an equation for the tangent line at a nice value near 2.1. All right, so I'm going to use x equals 2. All right, to write the equation of a tangent line, I need the derivative, I need a point, and I need slope. So we've got x, we need y, and we need slope. And then once we get that, we'll plug in 2.1. All right, let's go ahead and bring x squared out of the denominator so we can rewrite it as 6x to the negative 2. It makes the differentiation a little easier. Okay. And whatever your situation is, whatever the purpose is of what you're doing next, you might want to rewrite it as a fraction. Evaluate the derivative at 2. Cubed 2 and I got 8, and I'm reducing and I'm going to get negative 3/2. Let's get the y coordinate by plugging 2 back into the original equation. Two squared is 4 in the denominator, and that reduces to 3/2. So the equation of the tangent line going to be isolate y, and then we'll plug in 2.1. You might want to leave it in this factored form here. It's easier to calculate. So negative 1.5 times 0.1 plus 1.5. Without a calculator, it's probably easier to just change it to these decimals. Okay, this product is going to be negative 0.15. Add 1.5. 1.35 should be our answer. All right, well, I mean, I guess that's close. I mean, think about the functional value is 1.5, so 1.35 on the tangent line seems close. Here's a visual. Graph the original function. I don't know to how much scale this is going to be, but 6 over x squared looks something like this. It's pretty steep. Okay, my point is 2 3/2. So maybe something like over 2, up 1.5, maybe something like this. Draw in the tangent line, which is what you just found, the equation of the tangent line. Ooh, not bad. All right, and what's the functional value at 2.1? Well, if this is 2, then this is 2.1. Right here, I would intersect the tangent line first. So it makes sense that the y value that comes off the tangent line is smaller than the y value on the function. And that's all because the graph is concave up. And if the graph is concave up, the tangent lines fall below the graph. So I would intersect the tangent line y value before I get to the functional y value. So hopefully the picture makes sense. All right, we're going to skip 2 and look at number 3. All right, find a linear approximation. Aha, tangent line, point slope. Okay, I need a nice value. Well, 1.67 isn't close to 1, and it's not really close to 2, but that's okay. We don't need it to be. Look at the function. I don't want to make this 1 or this 2. I'm thinking about now in terms of pi, the unit circle, and I'm thinking that x can be pi over 2. That's about 1.5, 1.57. So that's closer to 1.67 than either 1 or 2. Now I need the y and I need the slope. Well, real quickly, I can find the y, plug in pi over 2. Sine of pi over 2 is, what, 1? So let's get the slope. Derivative evaluated at pi over 2. Well, the cosine of pi over 2 is 0. If the slope's 0, I have a horizontal tangent line. If I have a horizontal tangent line, this all goes to 0. The equation of my horizontal tangent line is 1. All right, so if I use this tangent line to approximate by plugging 1.6 in everywhere I see x, well, I don't see x. So my approximation on the tangent line should just be 1. Kind of strange, but let's look at a picture of that. Think about sine x. Think about the point pi over 2, 1/2. So that must be about right here, pi over 2. Sorry, pi over 2 and 1. So we're talking about this point right here. Well, imagine the tangent line to the graph at that point. It's going to be horizontal. So if this x value down here is pi over 2, then 1.67, which is a little bit bigger than that, is going to be to the right of pi over 2. And when I go up, I'm going to hit the graph before I hit the tangent line. If you're asked, the tangent line is an over approximation to the actual value because the graph is concave down. All right, that's all I wanted to cover on this note card. Now let's skip over to note card number 32. Properties of definite integrals. Okay, for this note card, the topic is properties of definite integrals. So if you need to revisit those properties, they're listed right here. Look at question 1. What are all the values of k, which is the upper limit, for which the value of the integral equals 0? Well, if our answer is 0, remember what we said as far as a property. We said that the limits had to be the same. So, I mean, if you're just going to reason through this, I mean, for goodness sakes, I mean, I guess k would have to be -3. All right, but our work is going to support that that's the answer. Because just in case we don't have a 0 here and there's some other number, and we can't connect back to these properties, we're going to need a strategy to help us find k, the upper limit. All right, well, let's find an antiderivative for x squared. X cubed divided by 3, good enough, evaluated from -3 to k. Don't forget, we're told that that's all equal to 0. All right, so we're going to do some work here on this side. We're going to evaluate at k and -3. So k cubed over 3 minus, plug in -3, cube it, divide by 3. Bring down the equal 0, or whatever number that happens to be. Notice back up here, I could have pulled out the 1/3 and put it in front. That probably would have made it a little easier. We'll go with this. All right. K cubed over 3 minus -27 divided by 3 is -9. Bring down the equal 0. Change this to addition. Continue solving. Subtract a 9 and multiply by 3. Subtract a 9. -9 times 3, -27. Extract the odd root. It's okay to have a negative under an odd root. Only even roots result in no solution. So it's just that your answer takes on the sign of the radicand. So my answer is -3. We knew it had to be -3 because we reasoned through it up here, but this is the way that you would, actually find the value for k if we didn't have that nice equal 0 here. All right, let's take a look at example 2. All All right, paying close attention to the integrands, notice that they're all the same. All right, paying attention to the limits, 1 to 10, 10 to 3, 1 to 3. It appears that from 1 to 10, that would be your entire integral. That'd be the whole. Now, let me switch these limits right here, and in doing so, we're going to make it its opposite. All right, the other two integrals would be the parts. Okay, so if I switch it, make it negative, and then I'm going to come over here and make this 7 negative also. So multiply both sides by negative. I could have done that one step, I suppose. All right, these are the two parts that make up this whole, so I'm just going to write a sentence involving integrals. The sum of these two parts has to equal the whole. This is the integral we seek from 1 to 3. 3 to 10 can be replaced with negative 7, and the whole integral is 4. Add the 7. The value of the integral is 11. All right, in the next several minutes, I'm going to explain note card number 43. But for some reason, I'm thinking that we have, at least in AB, we have already done this note card on a previous day. So why don't you flip in your clip notes and look at note card 43. And if you have something there, maybe just kind of run it back through your mind. Don't pay attention to the rest of this video if that's the case, or do if you want. Okay, in the next video, though, I'm going to look over the numerical integration techniques that we've learned in the past, the Riemann sums. Left, right, midpoint, and trapezoids. So watch if you want. I'm going to do note card 43. In the next video, I'll do note card 32B. Right. Particle motion summary. This is going to be a calculator question. Nice set of formulas here for us. Question 1. Given velocity, given an initial condition, we're asked to find the acceleration, velocity, and position of this little guy. All right, so I'm going to write this initial condition as S of 0 equals 2. All right, A of 3. It's a calculator question. This goes into Y1. Go to the home screen, necessary keystroke. Out pops this number. So what do we know from this? Acceleration is negative. The graph of the position function is concave down. The velocity graph is decreasing with a negative slope. Just different things you can think about. All right. What's the velocity at 3? Well, just go to the home screen and type in Y1 of 3. All right, so the velocity is negative. That means the particle is probably moving to the left. Well, he is moving to the left. All right, now once we find S of 3. That requires an initial condition and some integration. All right, after doing the integration and adding, and that should be a 3. I don't know if it disappeared. After integrating and adding the initial condition, I ended up with 1.58294. Done. Let's look at number 2. Is the speed of the particle increasing at time equals 3? Give a reason for your answer. So it's all about acceleration and velocity and the signs. They're the same. So yes, the speed of the particle is increasing. Take their question and make it your answer. Because V of 3 is negative, and A of 3 is negative. All right, question 3. It wants us to find all the times for which the particle changes direction. Justify your answer. Right, well, you've got the velocity equation stored in. You might want to do a zoom 6, a standard window. But remember, we're talking about time, and it does say time greater than or equal to 0, so you might as well just set a window with x min 0. And this is what I get. Some kind of graph like this. I think it might dip down and come back up, but I don't ever think it's going to cut through the x-axis again. This is our velocity graph. Looks to me like it's only changing directions one time. It's going from right, positive velocity is going right to left. So it says, find all time, justify your answer. Particle changes direction at t equals 1. And looking at the time, I want to save some. T equals 1 because v of t changes positive to negative. Okay, last question. All right, looking back up at the very top, find the displacement. Well, the displacement is just the change in the position, okay, from 0 to 3. Okay, well, if you look back at the graph, okay, the particle moves to the right slightly, and then it comes back to the left. Okay, so let's find the net change. Some of this positive is going to cancel with some of this negative. I still think my answer is going to be negative because there's more negative than positive, but we'll see what the integral tells us. Displacement is just the change, the net change. Calculations on the calculator, keystrokes of the calculator result in this. Total distance, okay, is going to be for us to consider how many steps to the right and how many steps to the left. So it should be positive. Look above, look at the formulas. Total distance can be found by taking any part of the velocity graph that's negative and making it positive. All of this would be reflected up so that we can accumulate. And when you perform this keystroke, you get this value. And as a reminder, if you're asked to write an expression for the total distance without using absolute value, you need to know that x-intercept. You need to know where the velocity graph changes from positive to negative or vice versa. So I'm going to integrate from 0 to 1. That graph is positive. Then I'm going to subtract the integral from 1 to 3 of the velocity. The value of that integral would be negative. So if you're asked to rewrite without absolute value, that's your approach. Okay, so I just wanted to review particle motion. So I'll see you in the next video when we talk about numerical integration.